On a number of occasions, I've been asked how big the squares are in the game OpenTTD, or how big the world is. Let's G-Sci then. In the game OpenTTD, you build up a vast transport empire using rail, road, air and sea transport. The game displays this world to you in an isometric view. This is displayed in the form of a grid and can be seen on the ground when playing the game. However, there is no consistency in the sizes of the objects in the game. For example, if you look at a road, it is about 1 square wide. But compare this to a football stadium which has 2 squares in width, which means the football stadium in width is only the size of 2 roads. Now, of course, that depends on the size of the road, but then you notice that the football stadium is actually 2 squares in length as well, which means our football stadium is actually square. That's not right, because football stadiums aren't normally square, they're normally rectangular, the same as the pitch. So what's going on there? Also, it breaks down further if you use an airport. Large airports in the game are only the width of 6 squares, which is about 3 football stadiums. I'd expect to be able to fit a lot more than 3 football stadiums in a real life airport. With no consistency in the squares, it falls to maths for us to work this out. The game tells us the length of the track, but this is just a number of squares. It doesn't really help us because there's no unit of measurement on it. On one measurement, the game does actually tell us that the height changes vertically in increments of 50 meters. So knowing that our slope goes up 50 meters, can we use this to work out the length of our square? No, we can't, because we don't have enough information. We'd need the angle of the slope or something like that to use trigonometry and work out the length of our square. So what do we know? Well, one piece of information we do have in the game is the date. The game gives us the time and date in the game. Also, it gives us the speed of our locomotives, so we've also got speed. So we have our speed, which we'll call S, and we have our time, which we'll call T. Now, we can use these in the equation for speed. S equals d divided by t. So in this equation, d is our distance, the distance we're trying to find out that the train goes along the squares. So let's get that information now. Here is our train in its depot. Let's set it on its way and follow it down the track. When it gets to this first road set here, we mark the date, the 9th of May 1976. Now, it reached its top speed of 128 kilometers per hour before it hit that marker. That marker notes a section of track here which is 100 squares long. Now, we don't know how long that distance is, but that's what we're trying to calculate. Once it reaches the end of that 100 squares, there's another road marker, and we can note the date that it comes to when it gets there. And here it is now on the screen. So, we started on the 9th of May 1976, and we're going to finish the 100 square section at 128 kilometers an hour at the 31st of May 1976. So first we need to get our T, our time. The difference between the two dates was 22 days. Now that's in days, but we want to work this out in hours because we're going to be comparing it with kilometers per hour. So we times it by 24, as there's 24 hours in a day. 22 days times by 24 is 528 hours. This is our value for T. So now we need to work out S, our speed, and this is easy because the train was going 128 kilometers an hour, so this is our speed S. We have T and we have S, so now it's time to find out what D is. So we need to get D on its own, we need to rearrange this equation. To do that, I'm going to times both sides by T, which gives us S times T is equal to D divided by T times by T. And when we divide the d by t and then times by it, the divide and times cancel each other out. The two t's cancel each other out on that side, which gives us d on its own, exactly what we needed. We'll flip over the equation to make it easier to read, and we get d is equal to s times t. Our s is our speed, so 128 goes in there, and our t is our time in hours, which is 528. So d is equal to 128 times 528. And if we times these two together, we get 67,584. This is the length that the train went in that time in kilometres. Now, we went 100 squares, so we're not quite finished yet. We need to divide this by 100. So 67,584 divided by 100 gives us about 676, rounded to the nearest kilometre. This figure is absolutely and utterly crazy. Not only is it hugely massive that each square could be 676 kilometres, but that would mean that our football pitch of 2 squares long would be well over 1,350 kilometres long. That is a very big football pitch, not to mention the houses that are absolutely and utterly huge. The scaling just falls apart completely. Well, this is a brilliant example about how all these sorts of things in computer games don't always work with real-life science. But OpenTTD is in some ways a simple game, but it has quite a bit of depth to it and can get nicely complex in a way that is quite satisfying. And the best thing about it, it's completely free. If you want to know more about OpenTTD, there's a cracking tutorial series over on the Master Hellish YouTube channel, and the link for that is in the description of this video, along with a link to the website where you can get OpenTTD from. Well, there we have it. Using the in-game date and the speed of the trains, we was able to do some maths and work out the size of each square, and the answer was quite ridiculous indeed. Thank you for watching. G-Sci out.